Okay, now, so the question is, what is a cosmic distance ladder? Okay. So, cosmic distance ladder can be defined as that each standard candle method can measure distances within a certain range. Collecting the data and measurements from each method allows astronomers to build a larger picture of the scale of universe, right? How big it is. This is known as the cosmic distance ladder. All right. Now, please write this down and let me know if you have a question. Now, the next thing we're going to do is basically called the Hubble's law. Now, Hubble's law states that the velocity of recession of a galaxy is directly proportional to the distance it is from the Earth. All right. So velocity of recession is written as v is directly proportional to the distance from Earth, and when we remove this, we get the Hubble constant. Now we'll get back to it after we learn about certain fate of universe. All right. Um, but right now, we need to remember this formula, please. Okay. Now, I just want to give you basically an order of magnitude, that how we can actually find and what method is there to find um, different, objects which are cosmic objects uh, from us. All right. So, keeping that in view, first of all, let's talk about, let's suppose this is our Earth, and one by one we're gonna, learn this. We'll go to Hubble again, so you don't have to worry about that. Just written the definition, just to give you an idea. So on Earth, let's suppose this is our Earth, and from Earth, if you want to basically look at anything near our solar system, then all you need to do is you need to put a radar, and the radar can basically see, let's suppose you want to see Venus. So the radar is going to send signals which gets reflected back on, radar catches it, so we can see Venus in our solar system. So usually the radar ranging, this radar ranging works best for 10⁻⁴ light years distances. Hello. जी अस्सलाम वालेकुम, क्वेश्चन था? वालेकुम सलाम। जी जी जी, वो मैं ज़रा ड्यूटी हो गई थी, तो मैं आपको ना कल, आज बता दूंगा रात को, आज ले नहीं सका वैसे ही मैं। जी जी ठीक, अभी नहीं, अभी क्लास चल रही है जी। ओके ओके, चलें, सही, शुक्रिया। ओके, so now you guys can see the screen, right, and hear my voice. Something happened, I don't know what. Hello. Gatika,
Yes, sir, it's visible.
Santik. Okay. Now, beyond this, so if we say this is till this radar ranging, if you're looking from Earth beyond this, so this distance basically is 10 light years. Okay. So then there's a method which is called the parallax. And parallax works best for 10⁻² light year objects. Okay, so it's basically a trigonometric, with respect to sun, we use trigonometry with certain stars in the background. Well, this method trigonometric parallax is not really in our course, so you don't have to worry about that. Just know that this is like for 10 raised to power light years. That's what it is. Okay. Beyond this, then, if you go further from Earth, like a couple of things I just want to tell you. So for Milky Way, we use the main sequence. There's a method called main sequence fitting. Again, we learn about it, but don't need to, really stress on it. It'll now be there. And main sequence fitting for the objects which are further away. Let me move it even up. When we learn main sequence, I'll tell you how it is. Just write it down right now. So it's basically for 10 raised to 5 light year distance away, like that. And then basically it's sort of, just make a diagram so you can relate it later when we're studying this. This is like clusters of stars that we see, okay, like that. Then we study nearby galaxies. Let me just put it here. So nearby galaxies which are basically 10 raised to power 7 light years away, and that we use with basically Cepheids.
So these distances are with respect to Earth?
Yes, of course. That's why I made the Earth first, right? So they're that away with respect to Earth. Those who don't know yet, light year is not time, it is distance. I'll tell you in a bit as well. So for Cepheids, we use there's a luminosity and there is a period, and then there is a line that we sketch using this. Okay, these are called Cepheids. Okay, after that I'm going to go down because then notes would not, they would be distorted. From Earth to a distance of say 10 raised to power 10 light years, we basically depend on type 1 1A supernovae, because there could be many. And there is one thing, we're not going to learn this, but it's called Tully-Fisher relation. Okay, so this basically okay, now so just remember that this is how we go further and further. And what do we need? Actually, we're trying to basically see through the Hubble constant that what is basically going to happen to our universe, that we're going to do in the last chapter right now. But this is how, with everything, we know that okay, standard candles really go really far from really far objects we can see from or determine distance from stand candles, that's why. All right, now, so these are all methods and combination that we use to develop the uh, it's like a canvas, we're adding more stars and more galaxies and everything together. All right, and I'll be just I'll be back in 1 minute. I need water. Okay. All right. Now, if we go back and what we've done till now, basically we read that unknown luminosity. All right. Now the thing is, how do we exactly find luminosity in any case? Okay. Because we know the radiant flux is the amount of intensity observed, right? So it's energy per unit time. We can find it through um, different spectrums. But how do we really find luminosity? That is related to two main laws. But the first law we're going to do is basically called the Wien's, and this is very, very important, so you guys should be writing this. Most of the questions will be related to this. Wien's displacement law. Now, so Wien's displacement law basically states that the black body radiation curve for different temperatures peaks at a wavelength which is inversely proportional to the temperature. Now, do not worry about it. There are a couple of words that you need to always write it. So the key word is the black body. Not this one. Wait. The black body and inversely proportional. Okay, so you got to write this in this definition. Basically, what it's saying is that from a certain black body, the maximum intensity, whatever the maximum intensity you receive, that wave will be called lambda max, is proportional to 1 upon the temperature at the surface. All right, now, so I'm going to just write this lambda max is the maximum intensity wavelength emitted by star. Okay, and here this is the temperature, basically the surface temperature of star. Now please write the definition of black body. So black body is basically is an object which number one is a perfect absorber and emitter of all radiations. So basically it can absorb and emit all sort of radiations, all right? And number two, it does not reflect or transmit any radiation. So it's not a reflector at all, so you got to remember that, all right? Basically, a black body, write a note here. Black body is an ideal star, all right? However, stars are the best approximation of it. In fact, it could be an ideal object. Don't write, it could be anything else as well. But however, stars are the best approximation because stars fall really close. Okay. Now, so what happens is that when you're looking at a certain star, suppose, okay, so it is basically sending you radiations of all kinds. So here we have intensity that you're receiving in watts per meter square, and here we have the wavelength. Wait. The wavelength lambda in micrometers for now, all right? So generally what happens is, what you see, that you see different peaks, like for example, you see a peak like this, then in fact I should have made it black. Okay, then you see a peak like this, you see a peak like this, see a peak like this, like that. This should be a bit forward, like this. Okay. Now, what you see right now is that this point for this peak means that this is the lambda max of, let's say, this first star. So there are different stars that we're looking at. This peak is basically lambda max of other, and then so basically the peak tells us what is the lambda, right? Now the higher the intensity is, the greater the temperature is going to be. So here the temperature would be like 6,000 kelvins. For this star that we're looking at, the temperature would be about, suppose, 5,000 kelvins. For a lower one, it could be 4,000 kelvins, and for the next one it could be 3,000 kelvin. So the greater the peak will be, the temperature, the highest temperature there is going to be, now the surface temperature is going to be higher. So generally what happens is that if you look at only the first one, this section wait a second, this section where the peak forms here, this section is of the visible light, because that comes in the highest intensity, and above beyond this, like before this, it's like ultraviolet, and after that it's infrared. So all sort of radiations are transmitted throughout this section, but it's just like what I'm saying is that this side is going to be violet in this, and the last one is going to be red, like this, and there will be 7 different colors as well. So violet, and where is indigo? Oh, I lost indigo. Okay, it's there. Like this, basically. So basically the whole spectrum of light shows here. So this is only for the one that I'm showing you right now, okay? That's not for the others. Just for your information, that is. I need to redo certain things actually. I may have made the red greatest, but chalo, it's alright. Okay, I just need to fill this up. Now it's perfect, right? So the point of all this is that basically you can draw spectrums from spectrum that you receive from sun, from receive from any star really. So you can find the peak wavelength. So this is the peak wavelength that you can find, and from that basically you can put it into this formula. You can compare it with sun's temperature, and you can find it find different values. By the way, Wien's displacement law has Wien's constant as well that we've developed in comparison to the sun, so it's not a big deal. So I'm just going to show you that as well, so that you know exactly what we are achieving here. So once you got this, so it means this lambda max will be equal to 2.9 times 10 raised to power minus 3 meter per Kelvin, and this is the temperature. So basically what we do is that we receive this by looking at the spectrum, and then we find the temperature using the Wien's displacement law. Is that clear, everyone? Abdul Moiz, Aman, Gatika, Hassan?
Absolutely, sir.
Okay, Suman. Just remember that this temperature that you're looking at is the thermodynamic temperature of surface of the star. So always take it in kelvins, that's what I mean. Okay, so you can take a screenshot. Obviously it's very difficult for you to draw this. I'll also send these notes once we complete the chapter, but for now just bear it.
the one at the top is a constant, 2.9 into 10 raised to minus
Yes,
3.
yes. This is basically Wien's constant.
Okay.
So generally we like to compare it. Like for example, if there are two stars we already know, right? So we say like for comparison, let me just write that too because that's gonna help you in a lot of questions for comparison. Lambda max over T1 equals to lambda max 2 over T2. So you can compare between, two different stars as well, their temperatures if you want to know. So if you already know someone's temperature, so and you receive a different wavelength for any other star, so you can find it by comparison like this. Do you get my point? Oh,
Yes.
no, my bad. I just wrote the wrong formula. Sorry. It's not correct actually. The formula is T1 and that's T2 like this. It's multiplied, not divided. Sorry. Okay, is that clear? Any questions now? Now, so here, oh my god, I just need to, I just need to do a question with you and little bit of writing, just small. Okay, so first of all, I would like to tell you, so write a note for this, that number one, shorter the wavelength at the peak intensity, so hotter the star tend to be. Usually, hotter stars are white or blue in color, whereas cooler stars are red or yellow, like our sun. Okay. So now the thing is that again with this, shorter the wavelength at the peak, then you can say that greater the intensity at each wavelength. As you can see that here the shortest wavelength is of the first line and it has the greatest temperature and highest intensity as well, so both of them you should remember. Anyway, now usually we have star classification done as well. So star classification is done by respect to a different mode of things, but we only are interested in color of stars and temperature. And this is for just comparison. They will give you this already, so you don't have to remember all of this, but just remember that blue is the hottest one, which is about 30,000 Kelvin as the surface temperature. Of course, Wien's displacement law has let us find this. Blue and white is between 10,000 to 30,000 kelvins, and then you got white, which is about 7,500 to 10,000. When the meeting ends, please rejoin the same link. Then Nadia, you never rejoin. Okay, so yellow and white are basically about 6000 to 7500 kelvins, and this is where our sun is yellow colored, and it's about 5000 to 6000 kelvins, right? And then it will turn orange someday, where it will be cooler than before. And then the last stage of sun is red, where it is going to be less than 3500 kelvins. All right, any questions, please let me know. Okay, right now yeah, please write it down. If you have a question, do let me know.
So we don't need to remember this, right?
No, you just need to remember the color with respect to how like it will be hotter or cooler, right? So you should know that blue is the hottest and red is the coolest, and then the in between.
Okay.
Okay.
Rigel.
Okay. Now let's do a question, huh? So the question says, the spectrum of a star Betelgeuse peaks at 828 nanometers, right? Whereas the surface temperature of Betelgeuse is 3500 kelvins. Now it says that another star, Rigel, in the constellation of Orion, peaks at 263 nanometers. Determine the surface temperature of Rigel. Alright, quickly do this, please.
So 11,000 Kelvin.
Yes, that's correct. So technically all you need to do is you just need to make the same lambda max t11 equals to lambda max 2 t2, and then one of them was 8 to 8. You don't even need to change anything. 3500, and this is 263, and this, so this comes out to be, it should come out to be 11,000 kelvins, right? So if they ask you that, okay, which color would Rigel be, what would you say?
Blue white.
Blue white, that's correct. Okay, so you have to just sort of remember the ranges, all right? Nothing else, nothing else. They're very gray. There's a gray area in this, so we don't exactly know. Because this is a very recent, just last year it started coming, so we don't know. All right, any questions now? Everybody's done? Everybody understands this?
So we could also use a formula, right?
Yeah, if that would be longer then, because then you have to, yeah, you could use that. That's true. All right. Okay, Abdul Moiz, Suman, and Nadia, and Aman. Everybody is clear, Hassan? Okay. So I think
Yes, sir.
so I would just would basically appreciate if you start completing the worksheets that I've given to you previously. So as soon as we finish this, which will be probably at the around 20th of December, for the next 10 days we're just going to do the worksheet checking, so that from the crash course we're basically prepared.